So now let's look at the interaction of this triangular well and the center RTD. So I'm applying a voltage of 0.42 volts. And in that voltage, I have aligned the center resonance with the emitter resonance 1, and it's under the emitter resonance 2. There's actually 2 bound states in this emitter. Okay? And later I will show some charts where I also trace this bottom of this emitter here. I call it BE. I will trace the Fermi energy, and I will trace the top of the emitter. Those are the critical energies to look at. Right? In the previous sections, we looked at the bottom of the conduction band edge on the left, and we looked at the Fermi level. Those were the 2 critical windows of energy, so to speak, right? Here, in a sense, we have the top of the emitter as a critical energy, and the bottom of the emitter here as a critical energy, and then all these resonances and Fermi levels, just like we had it. Okay? So now let's look at a transmission coefficient through the structure. So, since we're on resonance between E1 and C1, we see a very strong transmission. It's almost hitting 1. But I always said, well, you can't reach 1 in an asymmetric structure. That was for a single well. Here you have 2 molecules, so to speak, that are coupled. And they can be tuned in perfect resonance condition to transmission of 1. That is different than saying I have a single state, I put it in an asymmetric potential, and it can reach 1. So here, in principle, this could reach 1. You see a little bit of a bump in the transmission due to the resonance state E2, but it's down by 5 orders of magnitude on this log scale. Okay, so it's pretty small. And then you see a pretty broad resonance C2 that sits way up in the RTD. Now, if I crank up, if I look at the current, and again I have transmission times supply function on the left minus supply function on the right, I see a curve that is heavily modulated in energy. So this transmission here that looked very strong is now 4 orders of magnitude down. So current through C2 looks like 4 orders of magnitude down, right? Compared to the peak here at C1. But if I look at the current density as an integral already, I see a strong step function up to 80% of current flowing in C1, E1, which leaves about 20% of current flowing in C2. Again, this is a strong example of saying you can't estimate with your eyes the width of these resonances. I argued that the current peak here at C2 is 4 orders of magnitude down from this very strong peak here. But it's the proper integral over these resonances that matter. Okay? So even though this resonance is very high in energy, and even though there's very little supply function because the Fermi function is way down, there's a lot of current flowing there, 20%. Right? That's a significant number. And you can also see, since there's a strong step function at C1, E1, and there's not another step function at E2, that there's really no current flowing through the coupling of E2 off resonance through the structure. So there's this resonance E2 that sits here in the emitter, but it's really not contributing to current. It's sitting there, it has charge in it, but it can't supply current through the structure. So let's look at E2 a little bit more carefully. Now we take a smaller bias at 0.32, and now we're aligning C1 with E1. Right? They're aligned here. And you can imagine that now E2 can talk to C1, and there should be current flow. So now this is the transmission coefficient. So you see that C1 talks to E2 very strongly. There's a strong resonance here and a strong transmission. You also see a very narrow E1 resonance, right? So E1 seems to punch through the structure with a strong resonance. And then you see, again, transmission coefficient rising, and it looks like the former resonance C2 is really out of the picture in terms of energy. We're not resolving it anymore. And now I can show you the corresponding current density plot again. And again, we see that just like in the case before where E2 did not conduct, now E1 does conduct, basically conducts nothing. There is no step or increase in J in the green line, which is the running integral. And we see a strong step function at C1 E2 and nothing else. So under this bias 0.32 volts, everything is flowing through the E2 C1 connection in terms of energy. Okay? Makes sense? Now if we look at a current voltage characteristic that I will show you in the next slide, we have a strong rise in current up to a point of 32 volts. And then we see a drop. And guess what? At 0.42 volts, we see another spike in the current because now we're coupled again. So we're pulling this C1 into conduction and current rises. And then we resonantly couple to E2, and that's where the peak current is occurring. Then it's getting out of resonance, the current drops, and it starts to couple to E2 again, and it rises again, and then it drops again. Okay? What it means is you're starting to probe the resonances in the emitter. You have a bandpass filter, C1, and you pull it as a bandpass filter, and you see what you have in the emitter. And in this example here, current is not shutting off when the resonance is pulling under the bottom of the emitter, here and here. Current is pulling off, or turning off, once you pull the resonance C1 under E1. So the real supply function in the emitter is the resonance E1, rather than the bottom of the conduction band edge. So in other words, you have a quantum system in the emitter with a quantized state, and that determines your supply function. It's no longer the bulk conduction band edge. It's no longer this blue line here that's important. It's the quantized state E1 that determines the bottom of the band, so to speak. Okay?